Hello, everyone. Welcome to another Flan Talk. Today, we're excited to have Ruiquan Huang. He recently graduated from Penn State and is an incoming assistant professor at the University of Kentucky. And we're excited to have him talk about transformers and regular languages today. So please take it off.
Thank you, Andy, for the kind introduction. Um, yeah, so I think everyone can see the screen, right? Just zoom in. Cool. So yeah, I'm very glad to be invited to talk about our recent work called How Transformers Learn Regular Language Recognition. This is a theoretical study on training dynamics and implicit bias. And this is also a joint work with Professor Yingbing Liang at Ohio State University and my advisor at Penn State, who was recently moved to University of Virginia, Jin Yang. Okay. So yeah, so transformer has become the most important component in many modern AI tools since its invention at 2017. And um, but why it performs so good? This is a critical question we all want to know about the answer. So we consider this next token prediction style of the next token prediction style of learning. So basically, it says that given a sequence of token or or prefix x, it's a sequence of tokens, and want to predict the next one. So yeah, we basically want to learn from want to the transformer to learn such a output style. Yeah, there are many existing theoretical studies, many theoretical works to um, answer or to build the foundations of the transformers. So there are two types of works right now. The first one is mainly focuses on expressiveness power or in-context learning of transformers. So for example, there are works studying that um, one tension layer can perform one-step gradient descent. There also work telling us that transformer can do the work that statistician can do. And there also works studying the transformer can be simulated by a circuit. They're using circuit theory to study the expressiveness power of transformer. There are another line of works studying the training dynamics of transformers. So basically, it says trying to study how transformer can learn those tasks by studying how the parameters of transformers evolve during the training procedure using gradient descent. For example, there are work studying the regression tasks. There are also work studying binary classification tasks and also the next prediction. And in this work, we want to focus on the regular language recognition task. So it's also a specific form of a general classification problem, basically. Um, yeah. So a formal language is a set of strings all over the same alphabet. I have list some examples here. For example, if we only want to consider the alphabet to be a set of two symbols, A and B, and we say this language maybe we want to um, the legal language is that second to last symbol is A. So we can say that the if AA is a legal language in these rules, and for example ABA is not in this language, and we want the transformers, we want the model uh, to tell which whether the given sequence is in this language or not. We want to train the model, we want to train the transformer to learn such tasks. Okay, and there are also many well-known patterns are can be recognized or can be formulated as a formal language, such as palindromes or Python identifiers. And also, all the programming languages are formal languages. So that's why we want to study this formal language problem because it's so important, it's so widely used in our daily lives. Yeah. And there are two um, central or two critical problems in formal languages. The one is specification problem, is that how do we completely or precisely define formal languages? And second one is more interesting, is what we are interested in this work. It's called recognition problem. That is, given a language L and a string, we want to tell whether this X is in this language. Okay, and there are already many works. So there are many theories saying we can rigorously solve uh, the specification problem and recognition problem using deterministic finite automation for regular languages. So yeah, regular language you can see is as the basic language in Chomsky hierarchy. And so that's why it's basic. It's very important to study um, in many research problems. And in this work, we focus on two representatives of regular languages. So basically, regular languages are those who can be specified by regular expressions. And in this work, the first basic regular language is called even pairs. So the description is that the number of AB and BA is even. So we consider this binary sequence where the alphabet is the set of A and B. Okay, it's simple, it's basic, but it's important. So for example, this ABBA is in this language because the number of AB is 1 and the number of BA is also 1. So the total number is 2, which is even. So we say this is a legal language in the even pairs language. And AB then is not in the language because the number of AB is 1 and the number of BA is 0. So the total number is just 1, which is an odd number. Okay. And the second language is maybe more more popular to be recognized. For example, the parity check, right? We want to know whether the number of a symbol is even. In this work, we just say the number of B is even. For example, if we only have one symbol A, so then the number of B is 0, which is an even number. And if we have two B's, then of course it's uh, um, the number of B's is even. So it's in this language. But in the other cases, for example, if there's only one symbol B, which is not in this language. And if we have three B's, of course, it's not in this language. Okay, so we focus on these two tasks and we want to study how the transformer can learn those tasks and what's the behavior, what's the learning procedure of the transformer while doing gradient descent on these tasks. Okay. Um, so we first study the even pairs tasks. Okay. And while it seems more complex, but even pairs is equivalent to determine whether the first and the last token of the sequence are equal, right? So for example, if the input is just A, um, if there's only one symbol, the label is always one because there are zero number of A, B, and BAs. Okay, so that's easiest one. And for the other sequences, if the first and the last is not equal, then the number of A, B, and BAs are odd. Okay, so we set the label to be -1. And um, uh, So this is easy to interpret it because we have set the rule to be the total number of A, B, and BA. So if there's a change of symbol, then you can see that the number of AB has increased one. But if we change it back, then the number of AB and BA is even. Okay, so now the problem is equivalent to determining whether the first and last are equal. Okay, and so for such a task, it is apparently we need this position information because otherwise, if all the tokens are encoded in the same way for at different position, then it cannot tell whether this token is at the first or at the last, right? So we need some positional information, which is also popularly used in practical scenarios or in our real world life, real world examples. So we in this work we just manually encode the tokens in such a way that ensuring um, each embedding are orthogonal to each other if they are not equal and if they are not at the same position. So for example, at the first position, if the symbol is A, which is encoded as one at the first place and zero at the other places. Okay. And if it is B, then we will encode it as 0, 1, and all the other places will be 0. So as you can see, we divided the embedding to be basically if the length is, for example, here is 4, then the embedding dimension is 8, is the 2 times the maximum length. Okay, so in this work we just say there's a maximum length of the sequence, so the dimension of the embedding will be 2 times the maximum length. Okay, so as you can see, um, each block which has two coordinates will encode, will determine uh, will determine the symbol, and the position of the block will determine the position of the symbol. Okay, so for example, if we are at the second position, then the one appears at the coordinates 3 or 4. So for example, you can see if the symbol is B, then the one appears at the fourth coordinate, and otherwise it appears at the third coordinate. Okay, and for the third symbol A, the one appears at the third block, and so the one appears at the fifth coordinate. Okay. So basically, the symbol A, the embedding of symbol A at position L is given by the E subscript 2L minus 1, and otherwise it's E subscript 2L, and this E represents the orthonormal basis. Okay. So we also use this notation, the embedding of the symbol or token A at position L. Okay. And we consider this one layer transformer. Well, it consists of one attention layer and one linear layer. So say we have an input of X, which is a sequence of embedding, right? The length is capital L. And the parameter of this transformer um, consists of a linear layer U, which is a vector, because here we only consider a scalar output. And sorry, and a matrix W, which is a parameter of the attention layer. So here we just merge or reparameterize the transformer, reparameterize the KV and Q matrices, which would be the key and Curie and value matrices into one single matrix W, and value matrix into a linear vector U. Okay. And we also use this lambda to denote as the scaling factor, as in practically we just set it to be square root of d, where d is the dimension of the W. Okay. And here, because we only consider these decoder-only transformers, so the output will the Curie is just the the last token, the last token of the sequence, which is XL or the embedding of L. Yeah. Yeah. So the XL is just the the last token, the last embedding of the sequence. This E subscript L and superscript WL. Yeah. Okay. And we consider um, this loss function to be uh, right, to be written in this way, okay, as the standard the entropy loss, and it is averaged over the data set. Okay, so as you can see, yn is the label of the sequence, and xn is the sequence. And so you can see if it's a positive label, which means the x is in this sequence, then yn equals 1. So we want to minimize the loss, meaning that we want to let the output of the transformer to be a positive number so that we can minimize the loss. And otherwise, if x is not in this language, which means yn should be labeled -1. So by minimizing this loss, we are trying um, uh, to let the output to be negative. Okay. So basically, if the transformer is trained after the training is done, basically if the output is positive, we say we are predicting that the sequence is in this language. And if the output is negative, we are predicting the sequence is not in this language. Okay. And we consider this two-regime gradient descent method. So basically it says that there's a warm-up phase where at early steps we rescale the learning rate of the attention matrices of the attention matrix by the scaling factor. We use this lambda um, times the gradient of W. And in the later steps, we just remove this lambda. We just do the vanilla gradient descent. And this two-regime gradient descent is also can be viewed as an approximation of uh, of the atom, or like gradient descent with warm-ups. So, for example, in the adaptive gradient method, um, we basically we use the first momentum to be divided by the second momentum of the gradients, right? And because of this adaptively chosen learning rate, um, so as so at the warm-up phase, um, it is equivalent that this W will be updated faster than vanilla gradient descent, because you can see here we have a scaling factor in this model expression. So when we do gradient descent, if we times the lambda, then the gradient descent will be just like normalized one. Okay. Yeah. So before we introduce the results, I would like to uh, discuss a little bit more about the mechanisms inside the transformer, so we can know how transformer can learn and what happens um, inside the transformer. Okay. So say we have an input which is a three-lens sequence, right? We know that the attention layer will determine attention weights on each token, on each symbol, on each embedding. And then it will do a weighted average. Say, for example, if the attention weight of the first token is the largest one, okay, it's 0.7, and the other two the other two have smaller attention weights, okay, then we do this weighted average, and we time this weighted average with the linear head, with the linear layer U. Then we finally get an output, say, for example, zero point 0.6. So in this procedure, the attention layer will select the most important one, and then the linear layer will basically project these most important one to the output. So basically, the output, in other words, the output will largely be determined by the token who has largest attention weight. Okay, and of course, the attention weights are calculated based on the Curie token or the last token. Okay, so for example, if the atten we'll just call um, the inner product between the U and the embedding to be the token score. So basically, if the token score of the first one is more positive than the other two, and if the attention weight of the first token is larger, then the output will be more positive, and we say the prediction is the positive one. Okay. So after we understand this mechanism, we can prove that during the training, using such a gradient descent method, the parameters of the transformer will evolve in this way. Okay, so at first, the the token score of the first token, no matter what the symbol is, no matter what is, no matter it is A or B, the token score of the first token will always will grow at positively. Okay, and the token score of other positions will decrease, like to be negative. So this is illustration, not the actual value. So just illustrate that the token score of the first token will grow, and the otherwise they will decrease. Okay, and as you can see, because at the initialization phase, this learning rate is so small, so that this eta t is basically near between 0 and 1. So actually, the speed of the growing speed of the token score uh, is faster at the first place rather than the other places, the other positions. Okay, so this will enable us to characterize the dynamics of the attention layer. So it basically says that if it is a positive sequence, meaning the first and the last are the same symbol, then the attention layer, the matrix W, will put more attention weights on the first token. This is easy to understand because it's trying to predict the positive value of such a language. If this is a legal language, if this indeed has even pairs, then it needs a positive output. But we know that the token score is only positive at the first position. So it needs to put more attention weights on the first position so that the output is determined by the token who has largest attention weights, which is the first one. Okay. And otherwise, if it has odd pairs, the number of AB and BAs is odd, then it will put more attention weights on the second um, token, on the second position, um, no matter what the other token is. So this is this is because you can see that the token score at the second place is more negative than the others. So to minimize the loss, if it is a negative sequence or it is odd sequence, right? Then it needs to minimize the loss, it has to put more tension weights on the token who has the smallest value, who has the smallest value, which is the second token. And this is also because the second token appears more in the training procedure because it is at the second place. All the sequence whose length is larger than 2 will include the second token, right? So its token score will be trained more than the others. So that's why um, its token score is smaller than the others. Or in other words, its absolute value is larger than the others because it appears more in the training procedure. So then the tension layer will also put more tension weights on the second one. Okay, and of course, if the first and last are not equal, then it has the smallest attention weights, even smaller than maybe the third or fourth place. Okay, any questions so far for this initialization dynamics? Okay, good. Um, so you can see that um, right after the initialization stage, the transformer has shown its initial capability to identify the even pairs and the odd pairs. So in the second phase, it will basically do some just increase the classification margin by increase the norm of the parameters and and the value of the loss. Okay, so after the initialization phase, you can see the norm of the linear layer of or U will grow at the rate of log t. And also, we can use the implicit bias technique to say the direction of UT will largely remain the same um, with some ground truth direction. And this attention layer would not change too much because when the token score is too large, the loss is already very small, or the norm of the gradient will also decrease very fast. So the change of attention layer would be small than the first stage. Okay, so as you can see, if we plot we plot the token score and the tension score in these plots, and also the loss in the first plot. So um, there's a explicit two-phase dynamics shown in these pictures. While this green line represents the represents the first to second phase transition, while the red line represents when the parameter starts to just grow and the direction remains the same. Okay. So as you can see, after this red line, the loss will decrease at square root of t rate, and the this linear the linear head, the norm of the linear head will grow at the rate of log t. It's, because at this stage the norm of the gradient decreases like it's not that large anymore, but it still has some effect. So just increase the margin and minimize the loss. The loss just decrease fast. Okay. So any questions so far about the results? Uh, yes, these graphs are from synthetic experiments on some toy examples. For example, the length is just six or five. I don't remember the exact number, but it's a short length sequences with one layer transformer, just exactly the same as the setting we have just discussed. Like we use such a model, we use such a loss, and we use such a gradient descent. Yeah. Okay.
I have a question about the attention difference. Uh,
Mhm.
why the attention difference seem to increase after uh, like what does it mean? Like it seems like after you training more time steps, the attention difference is kind of like increasing.
hmm
But that means the model is not stable yet, or it's that
You mean even after 900 steps or
yeah.
uh yeah, it's increasing but it's starting to converge. So um you mean want to be I mean you mean you want to see like the
Like
curve starts to grow like in a
yeah
horizontal way. Is that
yeah yeah yeah.
okay? Uh, yeah, I didn't plot that too much long, but it starts to converge after like maybe like 1K steps. Yeah, just showing the dynamics of such parameters. Um, and as you can see that yeah yeah.
Okay.
So. Yeah. After too many steps, just
Okay.
converging in this way because it's for example, the setting is somehow clean compared to real world examples. Um, yeah.
Okay, thank you.
Mm. Okay. So the next task we want to study is the parity problem, which is also very important and there are many works showing that um, the neural networks or simply by applying transformer once cannot solve um, such an important problem. So first, um, the parity problem again is to check whether the number of bees are even or not. So here we would just want to consider the simplest form where just the 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 number of V in the entire sequence, okay, in the given sequence. So for example, if the input is A, the label is one, because the number of B is zero, right? Right? It's an even number, and if it is just the sequence just one symbol B, which means the number of B is one, which is odd number. So the label is minus one, and AB the same. The label is minus one because we only have one B. Okay, so let's see how deterministic finite automation solve parity problem. So basically, this DFA will maintain a state which will record um, the the number of bees at the current step. So we always initialize the DFA with state 1, and then we read symbol one by one. So say at time 1, we read a symbol A. So the state will remain the same because there's still 0 bees there. And at time t equals 2, we read the next symbol, which is B. Now because the state, we just at each step we just compare the state of the state of DFA with the newly read symbol B because they're different, right? We read a new B's here, so we just um, change the state to -1. Okay, and And then we read the next symbol, which is again B, but now the state is -1, represents already meet odd number of B's. So now I will change the state to 1 because after this newly read symbol B, the number of B's is even. So we just change the state from -1 to 1, and we just repeat such a step we just repeat such a procedure step by step until the last token. So the final state will be the final answer, indicating whether there's an even or odd number of bees. So this is how the traditional theory of DFA to do parity problem. So inspired by this, and our previously even pairs problem, we know that after training the even pairs, we know that transformer can indeed compare the first and the last token to see whether they're equal or not. And we also know that there's a technique called chain of thought in LM or in transformer that um, enables the logical model to think step by step and give the final answer at the last step. So this is pretty much similar to the DFA. So inspired by this, we can consider this two-step or finite step chain of thought to solve parity problem just using the transformer trained on even pairs problem. So here is how we do it. Okay, so say the input is ABB, which we know is a even which has even number of B's. So how do we do that? So first, we just compare the first and last token, which can be done by the even pairs problem, right? A and B, the trained transformer, after the training, it can already tell this is not equal. So it will basically output -1 or output a negative value, indicating they're not equal. So we just equate this -1 or equate any negative value with B, sorry. And then we just append this B at the last as the last token of the sequence, and now we can compare the second and the last token, right? This is just a mimic of the DFA. So we read the new symbol B's here, and we can use the transformer again on even pairs problem to compare the second and the last by cut the first symbol A. So we just compare B and B, which they're equal, right? So it will output a positive value indicating that the B and B are equal, and just equate the positive value with A, then we have our final answer A because we have read all the symbols after this step. The B is already be processed at the first step. So because A represents positive value represents 1, so it means it is a positive label, it means there are an even number of B's. So this simple design this some artificial design maybe because we need to um, output a symbol, append it on at last token, and cut the first symbol. So this manual design already indicates the power of chain of thought um, and transformer trained on simple tasks can already solve the more complex tasks. So this is a simple algorithm called truncated COT, which um, just process the sequence one by one and append the output and cut the first one. So by doing this, the trained transformer on simple problem can already solve the complex one. Trained on even pairs can already solve the parity problem. So can we do more? Can we, just train the transformer um, on both even pairs and the parity problem to, just not use such a other more like truncated COT, just use regular COT. And the answer is yes. So basically, you want to train the transformer with this chain of thought under teacher forcing, which is also quite widely used in practical scenarios where we just prepare the data set using chain of thought data set. So basically, we just uh, so how do we prepare that? Because we know that to solve a parity problem, we need to compare the first and last token one by one. So say we have an input sequence X, and what do we do at T step? So basically, we just consider the parity of sequence with length L0. We just maybe augment the data set to let the sequence all have the same length, L0. And then at first step, we want to compare W1 and WL0, right? The first and last one. And then we just, if they are equal, then we just, sorry, okay, yeah. If they are equal, then the label is one, right? And if not, the label is -1. And we'll append a new symbol A if the label is 1, and a new symbol B if the label is -1 to the original sequence. So for example, from xt to xt plus 1, which we have length L0 plus t. And we just repeat this step until repeat this step L0 -1 times because we have to read the symbol L0 -1 the number of L0 the number of readed symbol is L0 -1. Okay, so we just prepare the data set in this way, and then we can train our transformer using the data set, just again using these entropy laws. So here we have two types of laws, well, the form are equal, but the meaning of them are different. So at before L0, if the length is smaller than L0, we can view these as a regularization term while it is same as the loss function in even pairs problem. Okay, then after L0, which consists of the chain of thought data, uh, to solve this parity problem. So yeah, so there are two parts of the loss function, and the total loss function is just the summation of these two. Um, so we have two ways to see these. The first one is just like we train the transformer using COT data plus a regularization term. You can also view this problem as we train a transformer with mixed data set, consists of one parity problem and one even pairs problem. Okay, And we can also analyze the dynamics of transformer um, using the technique we just previously introduced. So at the first initialization stage, the token score will pretty much evolve similarly. So basically, it will um, let the first token to have positive token score, and the other tokens will have negative token score. Okay, this is also because when the length is small, we'll just do even pairs problem, and when we do even pairs problem, the solution will also be the same. And the difference is that for the tension layer, it will have different behavior compared to the even pairs problem. And we just so for length L for the length smaller than L0, which is similar to what we have seen before because it's a even pairs problem, right? We just uh, um, put the differences here. So when the length is greater than L0, so now because the task is not compare the first and last, but rather compare the last and the middle newly the symbol that should be proceed should be processed at the middle step, right? Because we want to compare the last token and the token at the middle point because this is the like DFA, this is the token where we are processing right now. So which we call L0, which equals the length of L minus L0 plus 1. Okay, so different from what we have seen in the even pairs problem, if they are not equal, the attention layer would put more attention weights on this token. Because previously we have seen that um, if they are equal, the attention layer would put more attention weights on the first token. But here it is if they are not equal, will gain more attention weights. This is because if we think about it, if they are not equal, we want to have a negative output, right? We want to have a negative output, but who has negative token score? We only have token score on the tokens who is not at the first position. So that's why we should put more attention weight on the token itself rather than the first one. So yeah, so there's a reason behind it. And similarly, if they are equal, now the tension layer is trying to compare the last and the token at the middle position. If they are equal, we want to have a positive output. But who has positive token score? We know that because the linear layer is assign positive token score on the first token, so it needs to assign more attention weights on the first token, no matter what the symbol is, because the mission of the tension layer is trying to determine whether L0 and L and the last token are equal or not. So no matter what the symbol of the first token is, it will always assign more attention weight on the first token. Yeah. So uh, basically, basically, you can see that the mission of the tension layer and the mission of the linear layer are very different from this perspective. The vision of the tension layer is trying to tell whether tokens are equal or not, which is the core part of these tasks, right? Of these even pairs and the parity check is to determine whether two symbols are equal or not. And the linear layer is just trying to somehow classify each symbols, whether just to give them a positive or negative value, and it's fixed there. It will not be determined by the pattern of the sequence. It's just about the token itself. Okay, and similarly, we can characterize the training dynamics after in the later steps. So similarly, the linear layer would grow at the rate of log t after sufficient number of steps. And again, it has some direction, it will converge. Okay. And also the attention difference score will just evolve at what we have characterized in the theoretical results. Okay. Yeah. So in summary, um, in this work, we have trying to answer how transformer is trying to solve regular language recognition by studying two tasks, which is even pairs and the parity check problem. And we show that as one of the interesting findings is that the transformer on simple tasks with designed chain of thought can solve more complex tasks, which demonstrate the power of chain of thought. And the second with chain of thoughts, with COD data, the train transformer can learn the mixture of simple and complex tasks, which again empower the transformer to learn what we cannot do them before using just simple neural networks or one-step output. So it says that by you know using chain of thought transformer can do more than we expected before. And this work was published at SML 2025 this year. And yeah, thank you so much. Feel free to just, uh, you know, uh, have any questions, just feel free to pop out.